Hello and welcome. Similar to the example I discussed on ns3 using CsmaNetDevices, basically what I have two LANs that are connected by a point-to-point routers in the middle. In this example, it's the third tutorial under examples tutorial third. This one uses a Wi-Fi on the other end and a point-to-point net device. And so we understand this part and this part. N0 here is an interesting one because it has a point-to-point net device and a Wi-Fi net device. And the way we create a Wi-Fi net device is more complicated. It is more complex. First of all, with wireless nodes, we need mobility. Nodes need to have a position so that signal is calculated properly. And in addition, Wi-Fi has separate implementation for the physical and MAC layer because of the complexity of the physical layer. There is a signal and fade over distance and so on. And the MAC layer, because we have different ways MAC implementation of MAC. For example, if we're using vehicular networks, it's a different MAC and it's different for access point and the regular stations referred to as STAs. So I'm going to skip the part with point-to-point helpers and CSMA helpers. We already know how to do that, and we set the parameters. For Wi-Fi, we will use YansWifiChannel helper. Notice that the Wi-Fi channels, Wi-Fi nodes will share a single Wi-Fi YansWiFi channel. And basically we're creating it with a default value. So basically the factory method sets the, as you can see it here, sets the propagation delay and the propagation loss to the default values. We could actually set that if we so desire with set attribute to something else. There are different ones like Nakagami or whatever it's called, and Friss and all the other ones. Also for the physical layer, we use YansWiFi physical. And basically we set the channel for this helper to this one channel object that is created. So only one channel object created for all the nodes. Then we use Wi-Fi helper. So this is where we actually install the Wi-Fi, as you can see it in this line here. AARF, what is it? Adaptive rate something. I think that's what it's called. AARF, I think it's adaptive rate Wi-Fi. AARF, I think it's adaptive rate control algorithm or something like that. But as specified by the method. Okay, this is the remote station manager. I usually use, for my vehicular communication, I use constant rate Wi-Fi manager. I think that's what it's called. This is your typical Wi-Fi, and one of them is an access point. So this one has different ways of how it communicates MAC implementation than the rest of the nodes because it's an access point. And so we created SSID, that's the name of the network that appears for Wi-Fi. And we have a MAC type. So there are different types of MAC for Wi-Fi. StaWiFi MAC, this is for the normal, the regular, your usual Wi-Fi devices, not the, except for the access point. Active probing, now with active probing, this is one thing that nodes do, probe requests and probe response. You have to know your Wi-Fi MAC implementation and how it works to understand these things. There's association, dissociation, all that, authentication and such. And so basically the station devices, which is stations are, everything, all the Wi-Fi nodes except for the access point, we'll do the install using this physical layer implementation and the MAC layer implementation and the Wi-Fi nodes. Okay? We can reuse this MAC object and basically set the type to AP Wi-Fi MAC, and the SSID is, the same SSID. And this really also uses the object factory method. If I look at the code, we could see that it has an object factory and sets the values. The most important thing here is mobility. Nodes have to have some sort of position, and you could set random walk, or you could set it as constant position. It doesn't matter. As long as they have a position, even if they were stationary, it will work. And so this basically creates a random pattern for the nodes to move within this rectangular boundaries. XY is a rectangle. And we also can set the mobility. And basically, once we do that, we will set that for the mobile devices, for the Wi-Fi devices, the stations. And then we reuse this mobility helper and set the mobility to constant position mobility model. So the access point need to have a position, even though it is stationary, because we need to calculate signal and such. The rest goes just as usual with our, just like the other examples. We install the stack, internet stack, we set IP prefixes, and we set the parameters to the Wi-Fi. The parameters for the UDP echo client and server. Now here we have a lot of traces also that we can use for Wi-Fi and Wi-Fi for Wi-Fi MAC and for physical Wi-Fi layer, basically. So there is a which includes signals and the such. Let me go to one thing. I want to go to WiFi physical. This is YansWiFi physical helper. This is the one I want. And I'm going to YansWifiPhy. So yeah, there we go. I want to go to the file WifiPhy. And I want to toggle source header. Okay. You can see all these trace sources and attributes: frequency, channel width, channel number. Some of these are set by default to their default values: TX gain, RX gain. There is a lot of parameters. There's a lot of things you can play with here. And you should know how you access your attributes by now, right? So / node list, star, and then device list, and so on. And in this case, it's a WifiNetDevice. Okay. I'm going to go to, for example, here is physical RX drop, and there is monitor sniffer RX. So this is an interesting one that I use. Look at how many things it have. Let me go to its declaration. So you can see it has the packet and a channel number and a transmission vector and the signal to noise ratio, dBm, the signal to noise. So you could actually print out the channel over which the packet was transmitted, received, and so on. To access this one, let me access monitor sniffer RX trace. Let me copy this. So what this does is a promiscuous trace. It fires for every for every packet being detected in the air, basically. Let's say packet here. I think this is channel. This is TX, and this is MPDU, and this is, let me say, SNR, something like that. So this is a signature. I also have a string context. How do I connect to this one? All right. And after we created, before we start the simulation, I am going to do config connect. Okay, we know this part. And we know here make callback. And it is called, what is it called? Monitor. I called it monitor. And I am going to go back here. I want this, oh shoot. I want to go here and put it right, where was I? Right there. So we have the node list, device list, and star, and I want to single out WifiNetDevice. Okay, monitor sniffer RX is in WifiPhy. So let me see if this can actually take me to WifiNetDevice. So I'm going to go to WifiNetDevice right here and look for the physical layer. Ah, look at that. We have a phi object which has the underlying value of WifiPhy, underlying type of WifiPhy physical. So I'm going to go back here and say phi. Oh, did I do? And I go and do phi physical. And then since this is YansWiFi, what is it called? WifiPhy, monitor sniffer is in there. Okay. So I'm just going to print things randomly. stdc out. I'm going to say context and std and L. And I'm going to then do /t. I'm going to say channel. And let me see what TX has. TX dot. So get channel width, get mode. Mode is interesting because it tells me the speed, the transmission rate. It's like the Wi-Fi mode used. MBDU, this is Mac unit aggregation. I don't want to do anything with that. It's not that interesting. Basically, it allows you to aggregate multiple packets. MPDU Mac, was it physical data unit? Packet data unit? Something like that. Mac protocol data unit. Yeah, there we go. And I'm going to print SNR. I don't know how you calculate SNR exactly. Let me say signal and then noise. Signal std no wait /t noise snr dot noise. Okay, all right, this should be fine and dandy. Let's try to run it. So it is WAF run examples tutorial 3rd. Okay, as you can see, we are transmitting at 6. Yeah, so these are the traces that I generate. There's a lot of packets. The reason is because even if the packet is not directed to you, it still picks it up. Okay, so the channel is 5. Is that channel number or channel frequency? I think it's the channel frequency. So it's 5.180 gigahertz. This is the transmission rate, the signal received, and the noise, and so on. And it tells you who fires it. So this is node 5, this is from node 6. They all will receive the packet. An interesting thing I can also print is time to show that packets are received in a slightly different time. Simulator now. And L. So I'm gonna do this time, and voila. So I bet you this is the same packet. You could see the time is slightly different. We are using sniffer Wi-Fi monitor. Basically, we are printing out everything, promiscuous trace. So you can see this one here is slightly, few nanoseconds, just like 4 nanoseconds difference of reception, because they're probably close to each other and the delay in the network. We could do a lot with these traces. I mean, if you remember, we did Ethernet header when we dealt with CSMA. In this case, I can do Wi-Fi MAC header. Is it Wi-Fi MAC header? Wi-Fi MAC header, yeah. Header, yeah, okay. It underlines it because it's stupid. HDR. No, it's packet, right? Packet that peak header and HDR. And then if the header exists, then I could just do STDC out. The Wi-Fi MAC header has 4 addresses, so I'll just print the first 2. So I like auto-completion, so I'm gonna basically when we import Wi-Fi model here or YansWiFi, it should import what I need, but it should do the auto-completion. So Wi-Fi MAC header.h. So now it should give me auto-completion. Look, it's all green, and it's packet peak header. All right. Dot get other one /t HDR dot get other 2 and I could do a lot more, so I could see what's going on. Let me do that /t. So what else is there? Get attribute, get sequence number. That's interesting. Sequence number, seq number. What else do we have? It's a good learning experience. HDR dot get duration. That's frame duration fragment. QoS TID. So this is which what priority queue is it? Was it get sequence control? All these different fields. Has data, is ACK. So you could. There's a lot of functions. Is beacon. I'm just gonna do is data. I'm just gonna do this like this. Is data. Else not data. Oh, we can have fun with it. I think this makes it work. Let's run it again. So now we have more information, sequence numbers. We could see that the packet is being picked by multiple nodes. There's a lot of things printed. Okay, that's where it starts. You can see this is a broadcast frame, sequence number 0. It's not data. I should add this space. This is the same one, the same packet, probably same sequence number. Sequence number has to do with the sender. So you can see this is the sender is A. So it's the same packet. You match the sequence number. This is from another sender. So this other sender has its own sequence number, and so on. Not data, not data, not data. Is there? I guess the first thing is ARP and figuring out IP addresses and such, but I don't see. All of them are not data. So I don't know how it's probably the way it was set up, but this is enough for this one. I think this is enough for a good experience. I had, here, no space here. So you could play a lot with it. You can monitor things at a very low level for your simulation. This works also for WaveNet devices, but it's a different signature. There is something called physical entities in WifiNetDevice. So, and you could also do the MAC layer. I'm not gonna do the MAC layer, but I'll just show it briefly here. So I'm gonna go to show the MAC layer for Wi-Fi. So for Wi-Fi MAC, so there is a Wi-Fi MAC and Wi-Fi, there's Wi-Fi MAC and there is Wi-Fi, what's the other one? Regular Wi-Fi MAC, AP Wi-Fi MAC. Actually, this is a very nice inheritance diagram here that shows you Wi-Fi MAC is the superclass of regular Wi-Fi MAC, and then we have ad hoc Wi-Fi MAC, infrastructure Wi-Fi MAC, mesh Wi-Fi MAC, and then OCB Wi-Fi MAC. This is the one we use for vehicular communication. AP Wi-Fi MAC and stationary Wi-Fi MAC. This is basically one is the access point and the stations connecting to it. So let me look at the trace sources for this guy. What's going on? Too big? Okay. I'm gonna just show them here. You can see all these attributes also. The slot time, this is for the back off slots and such, SSID. Those are the trace sources on the MAC layer level. There is also queues that you can access them just like we did with the TX queue. And I believe it is not implemented here. It's implemented in regular Wi-Fi MAC. So with the regular Wi-Fi MAC, I want to go to the trace sources and attributes at the end. For the regular Wi-Fi MAC, there is all these attributes. And which one is the queue? Can you guess which one is the queue? The queue is actually called TX up. This is how you access the queue, the non-quality of service, non-QoS queues. And these are the 4 queues. As you can see, queue that manages packets belonging to, yeah. But I'm gonna get into that when I talk about vehicular communication. That's about it. I'm almost over 20 minutes, so I talked a lot, but I hope this makes sense to you. Thank you for watching this. If you like it, if you learned something from it, I really appreciate that. Give me a thanks and a thumbs up, and ask questions if you are struggling with something. Thank you and have a good one.